All right, so, and I have to leave that open like that. So in your book, if you wanted something to read, go ahead and skip up to 1.5. That's really where I pick it up. The stuff about classification of matter and all the various stuff in there, all of that is so obvious, and it's going to be so obvious in about 4 weeks that you really don't have a place to put it in your head yet. So just for the sake of beginning at the beginning, textbooks like to start with that. But it's just kind of tedious and weird as a place to start as far as I'm concerned. It's very typical, and I'll do it too, in an introductory science class, especially chemistry or physics or a handful of other ones, probably engineering. The first thing you do is you don't, if it's a physics class, you don't go into physics immediately. If it's chemistry like us, you don't go into chemistry immediately. You know what you start with? You start with how do you do calculations. I'll bet you've heard some of this stuff before, significant figures, addition, subtraction rule, all that stuff. I think you at least usually get some introduction to that in high school. I didn't look at the little survey thing. Did y'all do the survey thing on there where I asked how many, have you ever been in a chemistry class? Raise your hand if you've been in an actual chemistry class before. Was it high school? Anybody do college? Anybody doing it again from last semester or something? So you've heard about significant figures. You've probably heard about the addition, subtraction rule, the multiplication, division rule. That's how you treat significant figures in a calculation. Scientific notation, also called exponential notation, where you do times 10 to the whatever. You've probably seen that somewhere before. So it's really kind of all that stuff. And in this class assumes you have you've had no exposure to that stuff before. So we'll just start at the beginning and kind of go through all that. Once we do that, then suddenly it'll feel like a chemistry class. So we'll talk about atoms and molecules, electrons and stuff like that. So I just wanted to point here to say, if you wanted to start reading somewhere, it's section 1.5 in chapter 1. And I guess all of these were as something to read, but I really think you'll get it from my PowerPoints more than reading this. So the book will be more useful later for reading and later for giving you problems to practice. Okay, so just to check to see that y'all can see the book. So what you should see on there is ebook, where our book is, syllabus and schedule. I'm not really done with all of that. Anybody do the safety video and the quiz? Okay. I think that's what's scheduled for lab. Maybe I should look. I'm used to doing the labs that we do in Dahlonega. It's the one thing that's different. I guess I should check that real quick. But I'm pretty sure, did y'all look? It's the movie and the quiz. That's all lab is today. All right. I think I can make use of lab, even if you've already done it. Lab schedule. So I can just as easily go over the syllabus in here for lab that I can for class, but it's just one syllabus, so I'm going to go over here. So the safety film and the quiz that's scheduled for lab today, you could have already done that. Did anybody not do that? Okay. Just by the time we meet Thursday, make sure you do that. I think you're supposed to pass that safety quiz before you're allowed in the lab. But truthfully, our next lab, it says math lab. That's still, we're right here at the beginning. We're still going through how to do calculations. So it's not even a lab where we get out chemicals. We'll go in there and we'll just continue with basically what we're doing here, just to make sure everybody's good with how you do calculations. If we're able to stay in here for lab Thursday, we might as well just stay in here. For any labs where we're not going to do anything as far as pulling out chemicals, if it's just an extra study session. But I don't know if this class is scheduled for anything afterwards, but that would go better in here. But I'll tell you what I think we should do in lab rather than watch the safety film, because you can do that outside. Any calculations that you feel confused about is what I think we should do then. So it's not until next week that we really start pulling things out and doing things for real in the lab. So anyway, so yeah, I guess I better get that. So so the next thing to do, so my syllabus, it's very typical that we just copy each other's syllabus and then change the names on it and any other relevant stuff, because a lot of this is just typical things that are in a syllabus. But the things you really want to know, I'm pretty sure this is the edition we're using, but it really kind of doesn't matter what it says here. You already have an ebook. So if you don't have that ebook, let me know and we'll figure out why you're not connecting to it. My office hours, so we have class in the morning, and then we have a break, and then we have lab in the afternoon, and I want to do my office hours after lab. So everything's done for the day and we can take whatever time you want. And I don't want to do it right after this lecture period, because I like to have a little time before lab to chill out. But I think it would work out if you have questions right after lecture and everybody's headed out and we've got an hour or two or whatever before, I can answer questions then too. If you really need a lot of help and you want to come for like an hour or so and just meet with me one-on-one, we can do that, but just email me and we'll schedule it and figure out the best time to do it, if you really need that kind of help. So I'm available for that. My office on this campus is a temporary adjunct office upstairs. I'm not sure if we need to meet in there. It's a decent enough room, and I guess I'll work on that computer in there in off hours, but I don't think we have to meet in there. I think we can do everything in here or in the lab. But if you do want some extended one-on-one time, we'll meet in there. So that's my office over the summer, room 211 upstairs. What else to tell you? On tests, you can use a calculator. I encourage you to use a calculator. But you have to get one that's that you can't program notes into and stuff like that. You know what I mean? Have you ever seen one of those?
So you can't use like a graphing calculator, like one of these?
Yeah, the big fancy graphing ones are the ones you can sneak notes into, so we don't allow those. You do want a calculator that you can use on the test for sure. Don't do this stuff longhand. But what you want for that is something cheap like these, that you can't put notes in and stuff. It has plenty of functions. It has everything you want. Go to Walmart, they're $10. You might as well have one. There happen to be a few sitting here that have probably just been left. There's 2 of these right here. Other than that, when you're doing homework, you want to practice with whatever calculator you're going to have for the test. But for sure, have a calculator. Don't try to do this stuff without a calculator. And this is just our lab manual. The lab manual is on there too, right? Course home. The only things you guys should see is the ebook, syllabus and schedule, safety video and quiz, and the lab manual. The rest of this should be hidden from you, and I'm probably not using any of this stuff. This is Dr. Driver's stuff that he let me copy, but I don't do my class anywhere near the way he did his, so I probably won't be using them. So y'all shouldn't see homework calendars, chemistry resources, PowerPoint, all that stuff you shouldn't see. If you do, you're welcome to look at it, but we're not going to use it. I need to just delete it probably. But I was going to look through it and see what he had. Okay, so the high points you want from the syllabus, it's not all this. Here's the course, here's the course description, and this is the course objective. Student will be able to demonstrate a good, okay, maybe you want to read that. Nobody really reads it, but we have to put them in there. Okay, I think I have this worked out right. The way the grades work, since it's a K course, your lab grade and your lecture grade go together into an overall grade, your grade for chemistry. The lab portion will be 25% of your overall grade, and then 4 tests and a final will be the other 75%. I will give you problems to work at home, and I will call it homework, but it's not for a grade. That's what you do to practice for the test. So your grades come completely from the tests, There's no homework, there's no projects, there's no discussion stuff, whatever. Your grade is based on how you do on the tests.
Will you still like review the practice questions and like?
Yeah, it's
Okay.
kind of like, well, that's what we spend time in class doing. You'll see how I do it,
Okay.
but I'll give you practice questions, and the deal is, if you can do those practice questions, you're ready for the test. There's no surprises. So the practice questions are practice for the test. There shouldn't be anything that confuses you on the test. I'll tell you this is what's on the test. And we'll go over the problems, and I'll show you how to solve the problems, et cetera, et cetera. That's what we spend time in class. So you'll see once we get started what I mean. So that's how I do my grade. I sometimes get talked into including homework for a grade, but I always regret it for various reasons. I was a student for a long time, and I like it this way. I like professors who did this because nobody looked over his stuff over the weekend, what D2L looked like over the weekend. Oh my God, there's discussion question 1, discussion question 2, there's this and that, and I'm just like, I hated that when I was in school. I'm just here to learn effing chemistry. What is all this crap, you know? I like professors who were like, you take 4 tests and that's your grade. You show me you learned it from me, and then that's all you have to organize your whole world around. This test coming up, got to be ready for that. Test 2 coming up, got to be ready for that. And all this other stuff, it just ate me up. I hate it. So I like doing it as a professor too, as it turns out. That's the way I do it. I think we have 12 labs, so 12 labs, straight up average is how you get that 25%. And I think I set this up correctly in the, I slapped this together Sunday night. Having said that, if test scores are low, I do this thing where I'll let you make up some points on your test, but what I'll do is look at all the tests and I'll decide what subject matter everybody seemed to have a hard time with, and then I'll make a little quiz out of it, a short 15-minute quiz that we'll do right at the beginning of class one day, and I'll grade that, and then I'll show you how that works if and when we get to that point. So there is a little leeway that you can, if you get a bad grade, might be a possibility of getting some points added. So I included that in the description of the grade here. Evaluation methods, course grading. I even do mostly multiple choice on tests. In some sense, that doesn't help you a lot, but in some sense, it does help. When it comes to at least test 1, where it's mostly calculations, you're still going to have to show a calculation to get full credit for those types of problems. But I might still make even those multiple choice. But if you don't do any math and you just go, I got a random chance of getting it correct, you won't get any points for getting it correct. So you have to show me how you got it correct. So we'll talk about test 1 as we get to it, though, what the structure will be. What else should I mention in here? This is still from Dr. Driver. I'll go through this and decide if these are the problems I want to do. So don't jump in and do these. Hopefully we'll be at a point either at the end of today or at the end of the day, Thursday, that I can give you a handful of things to go home and work on. But I just left it there because I thought maybe we'll use some of these. And I changed some of the other stuff down here, but I don't think there's anything else really important. No other requirements. I changed 1 or 2 things. Oh, this highlight here. Another thing I liked as a student is an instructor who would say, your tests alone decide your grade. Whether you're sitting here every day in class has nothing to do with what your grade. Well, it does. But if you could skip every single lecture class and still do well on the tests, fine. That's fine. If you can sit in here and show me you know this knowledge on a test, apparently you didn't need to be here. That's fine. It's fine. Truthfully, it doesn't really work that way. But that's my attitude on attendance for lecture. You can come or not. You're paying for the class. You're putting your time in to go into class, to be in school. And either you want to come to class or not. It's up to you. So Anyway, that's why I do lecture that way. Lab, though, lab, you have to be there because it's all about doing the lab work. It's all about you coming, participating, and actually doing experiments. So that's you can't skip. So you 100% have to be there for lab. You can come to lecture or not, but don't take that as me as encouraging you to not. I'm encouraging you to come to class, but I do take attendance for lab and lecture. Everybody sign this? But it's only because I'm required to. There's a handful of reasons why they want us to take attendance, so I take attendance and I can do what they want me to do with it. This chair is weird. So I think that's everything for my syllabus that really matters. I think the rest is self-explanatory, but anyway. Any questions about the syllabus or how the class runs? So that's the syllabus. I will get us a schedule like this put together. The chapters and what dates we'll be going over things. It'll be we'll follow it as closely as we can, but we may not follow it completely. But since we always start with this numerical stuff and calculations, I have my own way of presenting it, so I don't lean too heavily on any particular textbook for it. What else should I say in terms of introductory type stuff? What have I forgotten? Oh yeah, I should mention, I have mine. Actually, I better check into it. They might have these here. I've already lost them. I left them up in the lab. You guys ever take a lab class where you have to have the safety glasses? So I'll figure out what the deal is with that and let you know. Some schools provide them. They're just up in the lab and in a bucket. And some schools make you get your own, so I'll figure out. But we're not doing any real lab stuff until next week, so there's some time. I can't think of anything else process-wise. So suppose I'll start this. So I have these in two parts. What's missing from this is the addition rule, addition, subtraction rule, and the multiplication division rule. Somehow I forgot to squeeze that in. But I'll explain that as we go. By Thursday, I'll have some more of that. So, significant figures. Raise your hand if you've at least heard of significant figures. Okay. You have not? You have? Anybody has not heard of this? Well, I'm going to go over it from scratch, but were you comfortable with significant figures? Does it make sense? Really? Usually everybody goes, oh, I don't get this. You okay with significant figures? It all makes sense to you? I'm going to go over it anyway. So, the major rule when it comes to significant figures, or let me put it like this. Think about it like this as I explain this to you. Either you're the person who has to write down the significant figures, meaning you made the measurement and you have to write down correctly the significant figures. Or you're a person walking up to look at the data and you've got the numbers in front of you and you have to discern what are the significant figures that you're looking at. For now, think of yourself as the reader of the numbers. You're not responsible for writing those numbers. You're walking up to a piece of paper and those are the numbers on it. Think like that as I go through these next three. I think it helps to think about the two because you get confused for different reasons when you're trying to record the data yourself compared to when you look at it. And I'll say, the other note here says, what's confusing about significant figures is always the zeros. It always comes down to zeros. And here's my example. I did include a zero right here, but kind of ignore the second number. Here's a number, 1,121.32. How many significant figures you see? Every digit there is a significant figure. There's no zeros there, so it's not confusing. So that's 6. And skip this one. 3 digits there, that's 3 significant figures. However many digits here, that's 10. You see what I mean? Without zeros, there's no question. Those are all the significant digits. I say significant figures, I say significant digits. I think I say sig figs most of the time. Those are synonyms. So you can see how many significant figures there, and there's no confusion except for maybe the 57.60, and you're looking at that zero going, that's what confuses me. Does that confuse you? Do you sometimes look at these and go, I can't remember if you count that zero or not? You do? All right. I didn't see too many people mind. Usually people hate this stuff. Are y'all okay with significant figures? I mean, I'll still go through, okay, thank you. All right, so she shook her head. So those two big notes first. Non-zero, definitely part of the significant figures. Non-zeros, and that's the easy one. And the next thing to say is it's always the zeros that are confusing. All I've done here is I've taken these numbers over here and lined them up at the decimal. I'm not sure why. Well, I think I know why I did that. So there they are lined up at the decimal, and then this next one, it's still the same numbers, like this is still 1,121.32, but I've added some leading zeros and I've added some trailing zeros. And then I did it again, I just extended the zeros even further out. All right, so those zeros, so if you, let's say you made a measurement and it turned out to be 14.1, and you walk over to write it down on a piece of paper, you're not going to go 0, 0, 0, 0, 0. 14.100. You just never do that. You would not do that, right? You just walk over there and write 14.1. But technically, all those zeros are there, you know, in some theoretical sense. All those extra zeros, leading and trailing, they're there. You just don't write them. But when it comes to rules about zeros, the easiest one is the leading zeros never count towards significant figures. Of course, the leading zeros aren't written here. You typically wouldn't. Of course you wouldn't. But these leading zeros, those never count towards significant figures. We usually don't write them anyway. So that's the easiest one. All right. It's the trailing zeros here where things get confusing. Yes, it is technically true that there's an infinite number of zeros trailing all the way out to the right for all of these. But here's the rule. So now I'm going to pick out this 57.60 and play around with it. Okay, now we have to be the writer of the number for just a second here, but let me make a point. Can you see that? I purposely made that small because I don't want to zoom in. Can you see the 57.7, 57.6? So pretend we're measuring this purple bar here or whatever, and we've got our ruler here. We'll use rulers a little bit in lab for some things we do. Most of the time in chemistry you're reading a graduated cylinder, but it's the exact same concept. But this is what I'm describing here is actually true of any measurement. But if you look here, so you're measuring this and you've got your ruler here and you've got 57.5, 57.6, 57.7. And you can tell you're in between the 57.6 and the 57.7 for this measurement. What you would write down first is 57.6. You're definitely not going to write down 57.7. It hasn't risen to that level. But it's gotten to 57.6 and beyond. So it's definitely 100% true that these first three digits are going to be 57.6. There's no question, no way around it. Those are the first three digits here, because that's in between the 57.6, 57.7. You with me? All right, but you always do this when you're looking at a scale like this. You look a little closer and you pay attention to this space in between here. And these secondary tick marks, even if those weren't there, you could probably still see that this is just right at the halfway mark in between the major tick marks. Exactly between 57.6, 57.7. That's where this tick mark is. But even if it wasn't there, you could probably estimate that that's right around the middle, in between. Couldn't you, with your eyes? No special scientific equipment or anything, just your eyes. So yeah, probably the next digit you would write here is a 5. This is actually very close to 57.65. You follow? You're with me? Okay. Just to make the point, somebody might look at that, especially if that minor tick mark wasn't there, and go, no, I think it's a little beyond there. In fact, I want to call that 57.66. And maybe I wouldn't fight them on it. And somebody else might do the opposite and say, I'm looking up here, I'm talking about these. Somebody else might go, no, I think it's a little below there. I think it's 0.64. But here's my point. No one's going to look at this and go, no, it's crossing the line up here at 57.69. Nobody's going to make that estimate, right? Nobody's going to look at that and think that's anywhere close to the 9. See what I'm saying? If anything, if I took a random poll and I said, hey, what's the measurement here? And let's say there were 100 students in here, we're all going to be in these 3. There might be a rare one that just didn't really look very closely and didn't make a real method out of it. So here's my point. Or no, the point is that 5 that we wrote down, it might be perfect or it might be off by 1. But it's still pretty good. It's not just random. It's not like we don't know what it is. We're just going to guess and put a 5. We know we're close with that 5. Even if we're wrong by 1, we're only wrong by 1. See what I'm saying? So it's not a complete throwaway, that last digit. But let me go on here. Watch the purple bar. It's going to drop a little. Okay. Now what if we were here? Just so it's not so easy, it's not right there on the 5. This one's closer to 57.63. And again, I've done these purple ones over here to say, yeah, I decided it was about at 0.63, but you might say 0.64. Somebody else might say, I think it's 0.62. But nobody's going to say 6.9 or 6.8. Certainly no one's even going to say 6.5, really. I mean, look at where that tick mark is. It's obviously not right in the middle. Again, what I'm saying is, that isn't great, that digit isn't great, but it's still pretty good. It's not just a random shot in the dark at what it might be. So again, those first 3, when I first brought the ruler up and I said, it's definitely 57.6, at least that much is 100% correct. So this is absolutely certain, that part of this number. The only part that really has any uncertainty in it is that last digit that we estimated. But it's not terrible. We didn't just randomly choose a digit. You see what I'm saying? So usually when you're making a measurement like that, your first thought is, I thought this was science and everything was very definite, and you're making me sit here and make an estimate? Didn't that feel weird the first time in a science class? They're going, no, you got to estimate in between the lines and decide what it is. I'm just making the argument that final estimate in that last digit, A, it's always there, and B, it's not garbage. You're within 1 of being correct, very probably, right? Anyway, that was the argument, and then now I'm going to make, okay. So that ends up being 4 significant figures. That last one that we estimated, that does go with the significant figures. You keep that as a measurement. It's not a throwaway. That was my whole point. Is you can, even though there's a little estimate there, it's hard to be way off on that last one. So that would be a measurement that gives you 4 significant figures. And like I said, most of the time for this talk, I want you to think of yourself as the reader of the number and not the writer of the number. That was just a quick aside on here's what happens when you're the writer of this number. So that's 4 significant figures, and now let me make this one more point, because I'm talking about the zeros. Okay, and yeah, so the purple moves again. Watch it, moves down again. Okay, now we're right at that line, 57.6 line. And here's the point. You can look real close at that and go, you know what? I don't think that's right at 57.6. I think it's right here at 57.61. And someone else might go, no, it's just below that line. It's not 57.61, it's at 57.59. And then you go, no, I'm pretty sure it's right there at that line. If it's right there at that line, that's how that trailing zero shows up. And the whole point is, that's not just one of those theoretically existing trailing zeros. That zero was actually measured. That's actually a measurement. That it just happened to be right on the line. So for this measurement, we didn't just randomly decide we're going to throw a 0 there just because there's technically random zeros all the way out to infinity to the right. We actually measured it. We did consider this extra space in between the lines. And it turns out it wasn't in that space. It was right at the freaking line. That's how the zeros, the trailing zeros, show up in a measurement. So now again, think of yourself as a person going up and reading a 0, or reading a number, the 57.60. You see that in your list, that 0, all that 0 is telling you is the person who did the measurement, it would happen to be right on the freaking line. It was a measurement, that 0. You see what I'm saying? So the writer of this number, the 57.60, we trust that they know what they were doing. So you look at that and you go, oh, well, that 0 counts. That's part of the significant figures. That's why that's 4 significant figures for that number, because the 0 does count. So you're trusting the writer of a number to do it correctly rather than sit there and go, oh, that's the weird part, that 0. If that trailing 0 is there, it's a significant figure. It was a measurement. Makes sense? And when I say you're the reader of the number, on a test, on homework when you're practicing, everything in the following slides here, you're the reader of the number. You do get confused when you're the writer of the number sometimes. We'll be in lab, you'll be writing this up, and I'll be like, you should have a 0 after that, and I'll have to point it out. So you run into a different sort of thing that's confusing when you have to be the one that's recording the data. So I had to take a little aside for us to be the ones recording the data, but going forward, you're just the reader of the number now. So 4 significant figures there. Well, I guess I talked over this part. Yeah, 4 significant figures just happen to be right on the line. Okay, that's what I just said. And so I got another group of numbers down here with their significant figures out to the left. Only because I didn't have any of these up here that had all these zeros between the non-zero digit and the decimal, so I wanted to point these out. This is 4. This is 3 significant figures. This is 2. So here we are still dealing with zeros. All right, and I did this. I went ahead and extended. So this is by a convention. When you only got digits way down here, we always put a 0 here and a decimal, and then there's some zeros, and then you get to your first non-zero digit. But I've brought this tag back up, leading zeros never count. Realize these are the same types of leading zeros that these were. Right at the beginning I told you never have to deal with those. Those are never significant. You usually don't even write them. These are only written here because they had to. The textbooks usually say that's to locate the decimal, which sounds weird, but that really is the only reason those zeros are there. This is the, human beings all around the world for many a decade. This is how we write numbers, and this is how we represent decimals. So you kind of have to have those zeros there if you're going to write a number like this. And this is just me extending those zeros way out to the left. And this is what I'm saying. If you've got zeros, like if I'm standing here and I look to the left, and I see these zeros and zeros all the way out to the horizon, all the way out to infinity. And then I turn around and start walking this way, and I'm walking over zeros, and yeah, I trip over the decimal point, and I'm still walking through zeros, and then I get to my first non-zero digit, and I stop and turn around. If those are all zeros, those are the leading zeros. None of them count. So these situations, these zeros, these don't count for significant figures. They never do. These are still that same idea of leading zeros going way off into. So that's why that's 4. That's why this is. That's why this is 4. This is 3. This is 2. It's only these non-zero digits that count in this situation. You with me? So here I added some trailing zeros to these just to reinforce this same thing I've already explained. But I don't know why. But I didn't add a 0 there. I didn't add a 0 there. So these two are exactly the same as these. But pretend you walked up to this list of digits and you went, okay, now what are the significant figures here? I guess I did it. So they do actually change. Over here, my mouse keeps going away. So over here, I can see my mouse up there, can't you? You see my mouse moving?
Yes.
I'll bring a laser pointer. I couldn't find my laser pointer this morning. 4 significant figures here, but over here, you've got those same 4, but now there's 2 zeros. Those 2 zeros indicate somebody measured those zeros, so now it's 6. So it's those trailing zeros after the decimal, those do count. Same argument as before, the trailing 0 counts. If the writer of the number put that 0 there, remember, you're the reader of this number now. You walked up and you saw this, and you saw these non-zero digits. Those are definitely significant. But you notice the writer of this number put that there. Then you know they measured it. It's a significant figure. That's kind of redundant from what I've already said. Okay, so... okay, here's another situation with zeros, but this is actually easy to deal with too. So here's those original numbers I had over there, and all I've got right here is I've just replaced this 1 and this 2 with some zeros, and I've replaced this 7 with a 0, and I've replaced this 4 with a 0. A few 9s right here I replaced with zeros. I replaced this 8 and this 3 with zeros. The whole point is significant figures have to be contiguous. It's not like you can go, that's a significant and that's significant, that one's not, and that one's significant again. You can't do that. I mean, on that ruler I was showing you, there's the obvious ones that you know, those are the digits, and then you make your estimate for that last one for the 10 ticks in between these 2 ticks, and then that's it. You can't see any more detail. And if you can't see any more detail for that next digit, you sure as heck can't see any detail for the next digit. So significant figures are always contiguous. And I already said that non-zeros are significant. The fact that these 2 zeros are sandwiched in between non-zeros, they're part of the contiguous significant figures. So the fact that I've replaced some interior digits here with zeros, and I did it down here too, these got those. Okay, this is the previous slide. Look at the purple numbers on the left as I go to the next slide. None of them change. None of them change. All I did is replace some non-zero digits on the inside with zeros. And yeah, now those zeros are significant because they're on the inside of the contiguous set. So it's the leading zeros and the trailing zeros that I'm covering because those are confusing. But if it's sandwiched in between non-zeros, yeah, it's part of the measurement. There's no way for it not to be. So significant figures are always contiguous. So the fact that these zeros are sandwiched in between some non-zeros, then this whole series is still, this is the significant figures. So here we have 6, here we still have 4, here we still have 3, because I've replaced interior non-zeros with zeros. You with me? So it's all about the zeros for what's confusing, but sandwiched zeros, don't let that throw you off. I didn't sandwich a 0 here, I don't know why, I thought it looked weird. Oh, I couldn't because there was only 2. I threw these up there because I thought, okay, what am I missing? What situations am I missing? I think it's worth saying this out loud. This number, there's a 0 after the decimal. What that means is the writer of this number did measure that. It's like I said before. So this is for sure a significant figure right here because it's a 0 after the decimal that the writer of this number chose to put there. Remember, you're the reader of this number. So you trust they know what they're doing. They put a 0 there, that means it's a significant figure. It's not just one of those zeros that are theoretically there. They chose to write it, so it's a significant figure. This one, this digit over here, this 1, it's a non-zero, so it's significant. So these zeros in between, my mouse won't stay. These zeros in between, those are in between. Those are sandwiched in between two that you know are significant. That's why this is 4. It has to be contiguous. So actually all the logic was there before I got to this slide, but I just want to point it out. We know this is significant because the writer of the number put it there. We know this one's significant because it's a non-zero. Therefore, the ones in between have to be significant too because it has to be contiguous. That's a long way of saying that it's 4 significant figures there. You with me? The next one, I guess I've covered this, but those 2 zeros after the decimal, the writer of that number put them there, so they are significant. And of course, the 5 and 7 are significant. So that's why that's 4 significant figures. I'm not sure why I put these there. Maybe it's obvious. I guess I was trying to emphasize this leading zero doesn't count. So don't let that fool you. That's just by convention, we put that zero there. So anyway. All right, now we get to the weird thing. This is really just a convention. So again, you're the reader of the number, not the writer of the number. There's two situations you can have. If you have some zeros just to the left of the decimal, and further to the left there's some non-zero, like this, these, there's a different convention that shows up here. It's kind of an odd thing, but it's there. Okay, so this statement right here and this statement right here are identical. They're saying zeros just to the left of the decimal and nothing after the decimal. The writer of this number didn't put anything after the decimal, so that's the end of the measurement. There's no significant figures out here that they've hidden from you. You come up and read these, you know there's nothing after the decimal because they didn't put anything after the decimal. But just to the left of the decimal, there's some zeros. So there is a decimal there despite having no digits after it. And the difference down here is, of course, the missing decimal. And there's not even a decimal there for these. Okay, the difference is when you, my example here. So either you've made a measurement and you know it's needs to be three significant figures, or you're doing a calculation that we'll get to and you know that your answer has to be in three significant figures because of your input values. And then it's on your piece of paper, you've done your calculation, and right in front of you, you have 500. Or you've done your calculator, and what you've got in front of you is 500. What do? If it's three significant figures, you put the decimal there. If you knew it was supposed to be three significant figures, and this is the answer you came up with, 500, you put the decimal there to let the reader of the number know that those zeros are significant. I used a different example down here. I looked at it last night and I thought I made a mistake in it. So you made a measurement, you know it's three significant figures, or you made a calculation, you know it's three significant figures. Yeah, okay, and then your result has those four digits. How do you tell the reader of the number it's only the first three and not that last zero? Then you don't put a decimal there. Well, maybe this makes it obvious. With the decimal there, that's three significant figures, three, meaning these two are significant. With the decimal there, this tells you three significant figures. That means the zero counts. But down here, the writer of this number is telling you only one of these is significant. Only that non-zero is significant. These zeros weren't. They didn't measure. Nobody measures things to one significant figure, so this is kind of a silly example down here. That's why I pointed at a different one. You can kind of estimate anything to one significant figure if you're just looking at it. This 340 down here is indicating two significant figures because there's not a decimal there. So the writer of the number, you're trusting they know what they're doing. If they wrote 340 like that, you know it's two significant figures. That last zero doesn't count because it wasn't really measured. Makes sense? So weird twist there. There's one more really weird twist about this. I put even more strange. What if you needed three significant figures? I do this right, three significant figures. So the 3, the 2, and the 0 are your significant figures. And that last digit you didn't measure, how are you going to do that with this decimal game? You can't.
Would you do it with like scientific notation?
That's the only way you can do it, yeah. You predicted my next. So if you did it this way, you'd be telling the reader it's four significant figures. I'll get my laser pointer. But here you're telling the reader it's four significant figures. Here you're telling the reader it's two, but you needed three. There's no way to do it with this convention. You have to get a scientific notation, or sometimes called exponential notation. And we'll get to that. I might get to it today, but I might have to do it on the board. I think that's the end of this one. Calculations, part 1. I'll upload those on D2L if you want to look at them. It'd be great if this is just all a review for you guys. You don't really need it. That's part 1, here's part 2, okay. Calculations. All right. I'm not going to go into exponential notation quite yet. I am going to go over not the addition subtraction rule, the multiplication division rule. You guys remember that? Or at least you've heard the phrase. It just tells you how you deal with the significant figures when you're doing a calculation. You have your input values, and you're doing only multiplication and division in your math, and there's a certain thing you got to do with your answer related to what the significant figures were going into your calculations. So we'll do multiplication division rule, but I didn't say multiplication division rule explicitly here. I realized I was leaving that off as I made all these problems, but I'll say it as we go. But okay, first thing to say here, I will give you that on a test. I'll give you all those conversion factors. I'll give you this. You probably don't even really need that. I'll even give you this, the prefixes and all this stuff. Just be able to use them in calculations. But I'll give you that for a test. But let's look at what we have up here. There's in some sense 3 different types of conversions you might want to make, unit conversions. But let's start with English to English. We don't really use these in chemistry and science very much, but this is like, quarts, cups, gallons for volume. Length, you might use inches, you might use feet, you might use yards. Of course, we use the meter in science. But English, I call this English. This is sometimes called standard. So these are the standard measurements or the English measurements. And it's showing you the conversion between all these. You probably learned all these in grade school, at least most of them. One quart is 4 cups, that type of thing. 1 gallon is 4 quarts. All right, English to English. All right. So we went over all this about significant figures, but there's also this type of mathematical representation, this number that you might get that is exact. What we say it's exact. Like the integers are exact. Like if I said how many Coca-Cola bottle tops are here, and you would all go 1. And if you decided to write it down, you'd only put 1 digit. You'd go 1. But truthfully, it's like exactly 1. It's 1.0000 all the way out to infinity. Exact means it's zeros all the way out to infinity. That's what that is. It's not really just you would just write down 1. You wouldn't go 1.0000. But if it's an integer, it literally means it's perfectly exactly 1. It has an infinite number of significant figures. So that's what exact means. And really where the rubber hits the road is when a number is exact and it's in your calculation, you ignore it for significant figures. It's not going to determine your significant figures. Multiplication division rule is your answer has to have the least number of significant figures that your input values had. Do you remember that? So you've got several input values. And this one's 4 significant figures, and this one's 3 significant figures. The one with the least number of significant figures, you have to round back to 3 significant figures for your answer. That's why you ignore the exact ones. The exact ones are by far going to be the ones with the most significant figures. You're limited by the one with your least number of significant figures. So of course you're ignoring the ones that go out to infinity. You're looking at the ones that are actually finite. But when the rubber hits, where the rubber hits the road is you ignore your exact values when you're doing a calculation. You might have several input values and only a couple of them have significant figures to deal with, and the other ones exact, you ignore those and you only look at the, anyway, it'll make sense. All right. So what I've got here, I'm saying that everything in the English to English relationships up there, those are all exact. I mean, they're exact because that's the definition of it. One day, way back in yesteryear, someone had a gallon, and somebody said, it'd be useful to invent a new measurement that's 1/4 of a gallon. We'll call it a quart. They made it up right there. It's 4 exactly because they just made up the definition right there. You see what I'm saying? These are all, This one and this 12, there are exactly 12 inches in 1 foot. In fact, the definition of what inch is that it's 1/12 of 1 foot. Here's what I'm saying. This 1 and this 12, they're exact. That's 12.000 all the way out to infinity. This 1 is exact as well. My mouse keeps going away. This number is exact, this 3 is exact, this 1 is exact, this 5280 is exact. Every number in this English to English relationship chart are all exact. They're perfect all the way out to infinity. See what I'm saying? Different textbooks do slightly different things, or not in the English to English, it's in the metric to English. Okay, so every number in that blue box, they're all exact. The ones and the non-ones. In the, what color is that, brown?
Orange.
Orange, let's call it orange. So in there, the ones are exact and the non-ones are inexact. You have to consider the inexact ones for significant figures. So in here, this 1 is exact, and this 2.54, that's 3 significant figures. It's not exact. See what I'm saying? This 1 is exact. 39.4 is inexact. You have to consider those if you use that in a calculation. That's 3 significant figures that you have to think about when it comes to your answer in the calculation. You follow me here? So I'll give you this chart. I won't give you these boxes and these notes, but I will give you all this on a test. You don't have to memorize any of that. So in terms of doing calculations, you'll have that in front of you.
So the 2 and the 12 is not exact, I guess, or 12
2
inches?
and the 12,
Yeah, for 1 feet equals 12 inches.
these are all exact. Every numerical value in this box are all exact.
Okay.
And in this box, only the ones are exact.
I see. So it's just specific to that.
Yes. And the reason this arises is all these definitions were invented together,
Mm-hmm.
but this is 2 separate measurement worlds coming together.
I see, I
The
understand.
odds that they would actually be integers, multiples of each other, is just really low, so they end up not being. This is metric to English, did I say that? So you've got, so the metric system, you've got meters, you've got grams, you've got liters, sometimes we'll use seconds. The moles should be in here, but it's not in this list, but we'll get to the mole. So we have our length, our mass, our volume measurements. So up here in the English to English, there's length, there's mass, there's volume, and they have their own. But this is relating centimeters to inches. So that goes from the metric system to the standard. This one is meters to inches. This one is kilometers to miles. See what I'm saying? So these are all metric to English. The ones are exact, and the non-ones, now we have some inexact numbers. So if any of those go in our calculation, we can ignore the ones for significant figures. But any of those other ones show up in our calculations, we're going to consider those for our significant figures. The truth is, I see some textbooks that say, they'll tell you that's exact, at 2.54. I mean, if I peel back the curtain a little bit here, some of these, the engineering world has decided to consider some of these exact. It just makes things easier in their world. I think they're being silly, but we don't work in inches anyway, so I guess I don't really care. But as far as calculations on a test or something, I'm telling you to consider the ones exact and the non-ones inexact. If you're from some kind of engineering background that's driving you nuts, that's fine. It'll be okay. If you want to consider it exact, it's not going to hurt anything. I mean, if I call you out on a test and you go, no, I know damn well from blah, 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 that's exact, I'll be like, okay, that's fine. So don't go around agonizing over it. But in terms of deciding when something is exact and inexact, I'm telling you to follow those rules. It will help you to follow those rules rather than just let yourself be confused by it. So English to English, all exact. Metric to English, at least for the purposes of this class, the ones are inexact. No, the ones are exact, and the non-ones are inexact. They all happen to be 3 significant figures over here. That one's 3, that one's 3, that one's 3. That's 3, that's 3, I guess. I mean, these do have digits that go further out, but you have to stop somewhere for your relationship. So anyway, okay, so having said that, so there's English to English, there's metric to English, I include one more conversion, metric to metric. It's kind of weird to say that there's a conversion from metric to metric. In metric, there's only one length we use, meter. But in English to English, look at all these different measurements of length. There's foot, there's inches, there's yards, there's a mile. But there's only one when it comes to the metric system. So what are we converting when we say metric to metric convert? Well, it's this. Metric uses these prefixes that sort of fix the magnitude of things. And so I'm saying if you're given kilometers and asked to calculate what is that in nanometers, you're kind of converting between kilometers and nanometers, even though you're still in meters. So really metric to metric conversions are conversions among the prefixes, conversions among the orders of magnitude. So I'm going to do examples of all these, but just as far as rules to follow, all right. Conversions also, they stay within the same type of measurement. So this is a length to length conversion, English to English. I'll point out, so I told you in this box, these are all exact. I told you in this box, the ones are exact, the non-ones are inexact. Oh, I didn't mention that these are always exact as well when you do these. Everything in here are exact as well. You'll see why it's convenient to point them out. Virtually every problem you're given to solve, whether it's a physics class or chemistry or whatever, somebody has to sit there with a pen and paper and go, okay, I'm going to write a problem. 126.4, yeah, it'll be that. And that starts the problem. That's a completely arbitrary number. Everything in these boxes over here on the left that I've been pointing at with the mouse, there's nothing arbitrary about these. Those are the standard things. But this 126.4, I just made that up, completely made that up out of my head. Most problems have to have something like that that's just made up out of the blue to make it a problem. Those are always inexact. We have to count that one for its significant figures. We have 4 significant figures here, and you go ahead and assume it was a measurement somebody made. So you consider those significant figures. So that's the first thing to say for this question. So in a very orderly way of going about this, are y'all good with these types of calculations? These are kind of elementary, but I'll take you through a process because I think it's worth looking at this very formal process. For one thing, you're going to have to show me something for your calculations on a test, so I want to see something like this. But I'll take you through this process. It's going to seem a bit tedious, but this is a very formal way to do this. You look at the problem, you see that it involves feet and inches, so then you want to go over here and find the conversion for feet to inches. I wrote the 1 foot equals 12 inches right here, and yeah, that's a neat way to write it in a chart, but when you use it in math, I'm encouraging you to go ahead and take this and do it 1 foot over 12 inches. That's how you're going to use it as a conversion factor. Or honestly, it might be the other way around. You might be converting from if you're converting from feet to inches, you want to use this one. You want 12 inches on top and 1 foot on bottom. You see what I'm saying? So this is how this might be written in a chart or in text somewhere. But when you're about to use it for some math, you want to use it like this. Either like this with this unit on top and this on bottom, or the other way around. The number goes with the unit. So 1 foot over 12 inches, that's what we'll have here. Or you might have 12 inches over 1 foot. It just depends on the calculation you're making. And of course, in this case, we're trying to go from feet to inches. So I'm going to use the one with inches on top and feet on the bottom. That way, feet is going to cancel. You'll be left with inches. So this should be a very elementary thing to look at. In terms of just going slow and careful and being methodical, I came up when we didn't even have scientific calculators where you could actually put in the power of 10 times 10 to the whatever. Maybe you can even put units in now, but I would always do it this way on paper, so I'm going to go through these this way on paper. But for something like this, I at least want to see you set it up this way and do some calculating. But what I've done here is I've separated all the numerical values from the units. I've got the units over here and the numerical values here. 126.4, the 12, the 1, and the 1, I've got them over here. I like to separate these because you solve them differently. This you're just going to look at and cross out the feet and get to inches. And really, this is just a double check. You know you were looking for inches anyway. So this should cancel out to inches. If it doesn't, you've done something wrong. This is very elementary. You probably wouldn't mess this one up. It's when they get more and more factors in them that's more useful. But this is what you're going to do in your calculator. That's why I like having it all together. Sometimes there's power of tens that show up, and I usually separate those into their own section too. I have one like that. I'll show you in a little bit. But okay, so you do this. You take those numbers, you plug them into your calculator, and your calculator gives you something. If you put 126.4 times 12, that's what my calculator says. And I usually encourage you, especially if you're not comfortable with calculations, go ahead and write down everything your calculator gives you so it's in front of you. You know you're going to have to fix it up for significant figures, but go ahead and write it all down. Just remind yourself it's a different step. There's one more step. Is that chalk getting to me? All right, so that's what my calculator says. And now, once you've written down all those digits that your calculator gives you, now it's time to consider this stuff. I already told you that everything in here is exact. So the 12 is exact and the 1 is exact. This 12 and this 1, those are exact. I like to put this first value over a 1. That's just my way of doing it. Because I like to have, it just makes everything look very symmetrical. You got your numerator and your denominator. You can see right where the units cancel and everything. Don't let it bug you. I always put that over a 1. It, of course, equals the same thing as 126.4. But I stick a 1 down here. I don't put a unit with it. And that is, of course, exact as well. That's just the integer 1 that I stick there, just so that was obvious that that's the 126.4 is in the numerator. So there's your 4 exact numbers. So all you have left is that one inexact number. It's 4 significant figures. And what I usually do is, if I was doing it on a piece of paper, I would go ahead and underline the front 4 significant figures in front of me, just to remind me to go, those are the digits I'm keeping. But of course, you do one more thing. So the fact that there's only one number there that's 4 significant figures, we have to fix up our answer to be 4 significant figures. So you look at your significant figures. You do look one more digit out from your significant figures to decide if you're going to round that last digit. So we are going to look at the 8 to decide whether we have to round the last digit that we're keeping. And of course, the 8 makes you round the 6 up, right? So you usually round your way to the significant figures you want. You have to round your way up to your significant figure. So you look at that last digit out and go, does that round my last digit? Or you look at that next digit out and you go, do I round it? So yeah, you're going to round the 6 up to the 7 here, but you're not going to keep the 8, the position the 8 is in. So that's the number you'll come to. Do you follow all that? Very, very step by step. It's more tedious this way. If you have a quicker way of thinking your way through this, that's fine. But when it comes to a test, I at least need to see, this kind of process. You know what I'm saying? Just so you can prove to me that you can do the calculation. For this first test, there might be some this simple. There'll probably be a few of them that are this simple. Everything I'm showing you here today are all kind of simple. But there's one more thing to do. We solved this part. Now we have to solve this part, but really that's just obvious. You cancel the feet, you're left with inches, and then that's it. That's your answer. 100% correct answer with the correct significant figures. If I point at that and tell you that's 100% correct, does anything about that bother you? No? Okay. You haven't had that asshole for your chemistry class where they say, every time you calculate a number, you will put it in scientific notation. You never had a teacher do that? Scientists don't always put their numbers in scientific notation. They don't, so it's silly to say that. If I wanted you to put that answer in scientific notation, right up here in the instructions, you would say, put your answer in scientific or standard scientific notation. The fact that that's not here means that's 100% correct.
Is it a
I
safe?
saw you looking at me.
Yeah, I mean, is it a safe habit to form? I was gonna ask about the decimal, if I should put decimal at the end or not, but
Well, it wouldn't be wrong if you put the decimal there, but there's no reason for it. That convention about whether you put the decimal there or not,
Zero.
that's useful if there's a zero right here,
okay.
or a couple zeros right here. But yeah, the safe practice, well, shouldn't you just always put it in? Yeah, I guess you should, because you never know if your instructor is an asshole.
I never know, so I might as well.
But no, usually what they say is right at the beginning of the semester, they say that to you, and it's up to you to remember to make damn sure you do it. But that's silly. I'm not going to make you put everything in scientific notation, because we don't put everything in science. It's silly as hell to put everything in scientific notation. It really is. If I want you to get 12.5 milliliters, I'm not going to go get 1.25 times 10 to the 1 milliliters. I'm not going to write it. Nobody does. You'll see it over and over in the textbook and in your lab manual. Every number you see is not in scientific notation. So I'm not going to tell you to always put your answers in scientific notation. I'm going to tell you to read the question, and yes, I am going to ask you to put scientific notation some. You have to show me you know how to do it. I'm going to test you on it some. But if it's not there in the question, that's a 100% correct answer to this. The fact that it's not in scientific notation doesn't cheapen it at all. It's kind of silly to put that in scientific notation. So anyway, I'll go over scientific notation at another point, but that's the tedious step-by-step formal way of solving this very simple problem. Step by step. Here's where you stop and figure out significant figures. Anyway, so there could be one more step. Put it in scientific notation, but I don't want to do that yet. Here's another one, English to English. So over here, so it's quarts to gallons. So you look over here and you find the quarts to gallon relationship. You're either going to use it this way, or you're either going to use it like this, or use it like this. Just another example, very much like the previous one I did. I still separate my numerical values out from my units. I just think that's very helpful in terms of your thought process. Here you're going to put in your calculator 12.47 divided by 4. You don't have to deal with the ones. They don't change anything. That's what my calculator said after I did 12.47 divided by 4. And then you do this. Everything in that box over there, they're all exact, and that one and this one is exact. So again, we only have this one inexact. That completely made up thing I made up for this problem, those are always inexact. There's my 4 significant figures. This one turned out to be 4 again. The 5 rounds the 7 up, so what I'm going to put down for my answer is 3.118. Makes sense? And then, of course, the units. Cancel the quarts, you get gallons. And that's 100% correct answer. This one happens to be with the decimal in the right place. But, all right. Okay, now I'm going to do English with metric. Quarts and milliliters. All right. So what do we have? So we have one. This one that relates milliliters to quarts. All right, so I separated the numerical values again. 3.644 times 946. My calculator gave me that. Now I'm going to stop, now that I've written down what my calculator gave me. Okay, which of these are exact and which are not? So over here, I told you the ones are exact and the non-ones are inexact. So we're going to consider the 946 and the 3.644 for our significant figures. We have 3 significant figures on the right and 4 on the left. This means our answer needs to be in 3. Your answer is in the least number of significant figures than your input values. So I've underlined the 344, the first 3 digits, and the rest I'm going to round. We look at the 7, it rounds up to 4, round the 4 up to a 5. And notice I put the decimal there. I did that wrong. I did do that wrong, right? 3 significant figures. Did that wrong. Right there. Right? Right. Yeah, 3 significant figures. Did I do that right? Somewhere around 450. Yeah, that's right, isn't it? Y'all checking my work? Yeah. So another example, but now involving some of the metric system stuff. And of course, the courts cancel and you've got your milliliters, and that's the answer. I guess I have to fix every page where I have that. All right. Save. You got a 1245, is that right? Hmm?
Yeah, 12:45.
Okay, so another English and metric conversion. So I just made up a number, 347.2 inches. How many meters is that? And you do have an inches to meters here, so we'll use that. I'll skip down here. So 1 meter is 39.4 inches. Put my numerical values together. 347.2 divided by 39.4, my calculator gave me that. Once you write down all those digits your calculator gives you, now it's time to consider your significant figures. This is why I say just go ahead and write them all down and just do this step by step. You do it this formal way, you can't go wrong. So those are the exact numbers. The one from this box, and then the one that I just used to prop up the number, and then the 39.4 is 3 significant figures, then you got 4 significant figures for the 347.2. I think I was avoiding zeros because I thought I was going to explain that later. So you haven't gotten practice with that. So it's 3 significant figures. I've underlined the first 3 of all those numbers my calculator gave me to remind myself those are the ones I'm keeping. I am going to look at that 2 and see if it rounds up to 1, but it doesn't. So that's my answer. And of course, you cancel your meters, you get your inches. How many meters?
I was gonna say.
Yeah. I'll copy and paste this. So yeah, I need to fix this too. Should be 2 inches over here. That's a lot to fix. Yeah, I did the units. Weird. I'll go back and fix it before I upload it. Y'all see what I did. I had meters and meters and inches here. It should have been inches on top, inches on bottom, and meters there. So I got messed up when I made this. I'll fix it before I upload it. 34.7 centimeters. How many milliliters is that? Millimeters. Or centimeters and millimeters. Okay, yeah. So now we're to the metric to metric, and like I said, it's weird because we're staying in meters, but we're really converting between the prefixes. How are you guys at doing these? Knowing that I'm going to give you that chart. Really, y'all are good at these? I'm going to take you through the tedious algebra. So I'll show you this formal way to think about it. But so if you have trouble doing a calculation like this, follow along what I'm doing. I'm going to do every tedious algebra thing you could do. The totally made up number, invented number for this is 34.7. I just decided it'd be 34.7 centimeters. And now you have to report how much that is in millimeters. You can go ahead and set it up like this, knowing that you're going to need a conversion factor here that takes you from centimeters to millimeters. That's what this is asking for. And here's the way I like to explain this. So if you look at this chart, think about it like this. I'm going to say meters, but this doesn't have meters, it doesn't have grams, it doesn't have liters, it doesn't have any of those in here. But it means decimeters, centimeters, millimeters, if you're talking about meters. It might say decigrams, centigrams, or milligrams if you're dealing in grams. What are we dealing in? We're dealing in meters. So let me just say it like this. Are y'all all good with this? I'm going to say it like this just so you know, but I need a relationship from centimeters to meters. That's in here. So this is centi. So 1 centimeter equals 10 to the negative 2 meters. The base unit goes here, and then your prefix with the base unit goes here. It's always a 1 here, and it's always this value with the base unit. If y'all are comfortable with those, I won't harp on it, but no. So here I've got 1 centimeter equals 10 to the negative 2 meters. That's not in here anywhere. You don't see that. You see 1 foot equals 12 inches. You see 1 meter equals 39.4 inches. But you don't see anything down here that says 1 centimeter equals 10 to the negative 2 meters. So what I'm saying is the 1 centimeter, it's 1 centimeter equals 10 to the negative 2 meters. That's how I got this. So if y'all are comfortable with your way of doing this, that's fine. But which means I'm either going to use it like this, 10 to the negative 2 meters over 1 centimeter, or I'm going to use it like this, 1 centimeter over 10 to the negative 2 meters. Of course, I'm going from centimeters to millimeters. So also need a relationship between millimeters and meters. So I'm doing this the really tedious algebra way. If you have a way of doing this, that's fine. What I'm doing with these, I wouldn't expect you to have to show me on a test. But the point is, 1 millimeter equals 10 to the negative 3 meters. That's what I've got here. And I'm either going to use it like this or I'm going to use it like this. So what I need is a conversion factor that has millimeters on top and centimeters on the bottom. So I can take these relationships and go, this is the only one up here that's centimeters on the bottom, and this is the only one up here that has the millimeters on top. I'm going to pluck those two out and start messing with that. I've got a relationship of millimeters to meters, and I've got a relationship of meters to centimeters. And I've got these set up where the meters are going to cancel, and I'll be left with millimeters over centimeters. Yeah, that's what I want, millimeters over centimeters. You probably have a better way to do this, but I'm just showing you all the algebra that gets you there. So I'm going to take that, I'm going to do what I did before, separate the numerical values and the units. You can kind of ignore the ones, these ones, but what you do here, so I'm taking this bit out and pulling it out without the ones in it. When I'm going to move this 10 to the negative 3 to the top, when you move the 10 to the negative 3 to the top, you change the sign. So it's just a simple algebra rule, but it's one that's easy to forget. When I'm taking this 10 to the negative 3 and put it on the top, and change its sign, so now it's 10 to the 3. So that's the step I did between there and there. And then, of course, you probably know this. The math that you're going to do here is it's just this simple arithmetic on the superscripts on at the exponential number. So ultimately, you have 10 to the negative 2 plus 3 is 1. So ultimately, what I'm down to here is 10 to the 1. I can just write that as 10 over 1. I'm going to leave it in this fraction form instead of saying an equal sign and saying 10, because I want this. I want an upstairs and a downstairs. So again, if you have a better way of doing this, you can do it your way. I'm showing you the pure algebra way. So here's my 10 over 1. Now I'm going to do the units. I cancel the meters. I've got millimeters over centimeters. Ultimately, that's saying there's 10 millimeters in 1 centimeter. I know that was a long walk. If you have a better way to do this, to find this conversion factor, you can do it your way. But ultimately, now I found this. 10 millimeters is 1 centimeter. I've replaced the 34.7 centimeters to here, and now I've filled in my pound sign for these. So here we are, 34.7 centimeters. You've got your conversion factor. You can find it in millimeters. Again, I separate the numerical values from the units, so I'm canceling the units separately. And of course, 34.7 times 10 is just 347. And I had to remember to back up and tell y'all, all of these are exact. The only number on this whole page that is not exact is this 34.7. When you're in the metric system, converting metric to metric, everything's exact, except for that one made-up number that the writer of the question had to invent. So that's the answer to this, 347 milliliters. And again, I'm not dealing with scientific notation. It doesn't ask you to put it in scientific notation. There's absolutely nothing wrong with that answer. 347 millimeters is just the answer. Okay, I've got one more of these conversion types for metric to metric. Here we're going nanoliters to megaliters. So I've picked out nanoliters to liters, and I've picked out megaliters to liters to work with. Again, if you have a better way of doing this yourself, that's fine. So I get here, and then next, I'm going to take these numerical values here, 10 to the negative 9 over 10 to the 6. I bring the 6 to the top, 10 to the 6 to the top, so it's 10 to the negative 6. Keep going with your arithmetic. You get 10 to the negative 15. I'm going to leave it as 10 to the negative 15 on top with a 1 on bottom because I've got to incorporate it back into that conversion factor. So there's your conversion factor. 10 to the negative 15 megaliters is 1 nanometer. So now we can complete this part of the problem. Separate your numerical values, cancel your units. Okay, and in this case, watch this. That 10 to the negative 15 just showed up naturally, and I'm just going to put it in the answer. 34.7 times 10 to the negative 15 megaliters is the answer here. All right. What do I have here? Oh, so I circle it in orange. I started to put together something here. But I think I'll do this on the board.
Is that answer technically correct like that?
Yeah, I knew it would bother you. So now I'm going to segue into, where the hell did he come from? Now I'm going to talk about scientific notation, also called exponential notation. Let me make sure. Okay, that's still going. Sometimes it just shuts off, so I need to keep an eye on it. So as long as you can see me here, y'all tell me if this shows up on the video. Which one of these shows up best?
No,
It's gonna be a white
Oh my God,
only see the yellow, barely.
or yellow. Yeah.
that's the yellow.
Try
right
the
there.
white. You got it on your left.
No, that's the yellow. Huh?
I said try the white one on your left.
Oh yeah, good. Yeah. There's this white one.
Wow.
All right, that did nothing. Well,
Wow. All right, let's see what this sucker does. I bet that's.
Okay, there we go.
Somebody's already thought about this. What shows up on the video? I'll use that. So yeah, the video's working. Let me bring this back up. So that bothered you, huh?
just a little bit.
Okay. I'll use that value. Now, well, let me do this. That's not going to show up. Times 10. guess I want to do. And I'll do this to 6. Oh, yeah, I miss having a whiteboard now. This feels weird. It's 10. Is that showing up on there? My writing isn't that messy on the whiteboard. All right, I guess that's good enough. All right. Okay, hopefully that looks good. All right, so every one of these equal each other. They all equal the same thing, right? All of these equal um, 10 to the 0 equals 1. So this is 1 times this, so it's just this. Oh, writing on the chalkboard sucks. All right. All of these numbers are in scientific notation. They're all in exponential notation. That's what bugs you, right?
I was just taught that only one of those is correct.
Right. This one is special. It has the decimal in between the first digit and the second digit. So all of this is scientific notation. That is standard scientific notation. I make a big deal about it because textbooks get this wrong, instructors get this wrong. If an instructor says, put your answer in scientific notation, put it in standard scientific notation, because that's what they meant. And you don't want to get in an argument with your instructor. So, at the end of this calculation, yeah, that's scientific notation. We happen to land in scientific notation. The 10 to the negative 15 showed up kind of naturally, but it's not in standard scientific notation. All right, so if I want to put that in standard scientific notation, I'll show you another very formal way, algebra way to think about it. Man, I don't like the chalkboard. So 34.7. To the negative 15, right? Let's say at the top of there it said, put your answer in standard scientific notation, and now you have to do that. So to put this in standard scientific notation, what do you get? Those of you who are good at this.
3.47 times 10 to the negative 16?
Okay. Are you sure it's 16?
No?
Good. Here's how I tell you how to do this. No textbook and no instructors ever told you how to do it this way. First,
Oh, wait, no, I am not.
you might have been right. I didn't even think twice about it. And you can do it your own way. I just like to show you this algebra way. So first let me make this point. What does that equal? 10 to the 1 times 10 to the negative 1. Well, all of these equal 10 to the 0. You get there first. You do arithmetic on the exponential number, the superscript. Exponent, thank you. Those are all 10 to the 0, but 10 to the 0 equals Actually, anything to the 0th power equals 1. These all equal 1. And of course, I could go on and on. I could go 4, 10 to the 4, 10 to the minus 4, I'd still get the same thing, 10 to the 5, 10 to the negative 5. You with me? What I tell you to do is rather than think, am I adding 1 to this or am I subtracting 1 to this? Don't even think like that. Look at your decimal where it is and count how far it is to get it to where you want it. Here, we only need to move it 1 space. Don't think negative 1 or positive 1, just think it's 1. I'm going to separate these times 15. And I said 1, right? 10 to the negative 1 times 10 to the 1. All I've done is multiply by 1. You can't just willy-nilly move this decimal around. It changes the value. That's why you're thinking, you're double thinking and trying to fix up what you're messing up by changing this correctly. Multiplying by 1 is not going to change the value. So you're free to just throw in here 10 to the negative 1 times 10 to the 1. Or I say 10 to the negative 1 times 10 to the 1. And then if I put some parentheses around things, I'm going to take this and go ahead and do that math. That's going to give me 1.7. This part, this much, gives me 3.47. And what I have left and of course, now all you have to do is this bit of math. Plus 1 minus 15. So it's negative 14. That's what you said, though.
No, I said 16, but
You
I
did?
realized I corrected myself and said I was wrong.
Good. But you see, you don't even have to think now. You just put these in. All you decide is how far do I have to go. Don't think positive or negative. And then just put that in. That's why it's 1 and negative 1. We only had to move 1. So I did times 10 to the 1 times 10 to the negative 1. And then I took the 10 to the negative 1 and applied it here so I could get the value I wanted. Now I'm left with that, and it's just that last simple step. 3.47. You can do it your own way. If you can do it quicker than that, I don't even have to think when I do it that way. I don't know if she was right or wrong when she said 16. I get it wrong when I try to do it that way. So I like this pure algebra way of doing it. But I'll put some of that type of stuff in a PowerPoint. I just don't have it in one yet. Okay. What I want to do. Let's see if we can find. We might have to take breaks in the lecture. It's hard to talk this long. What was I going to do? Oh. Textbooks, to me, are notorious for having just the worst possible questions they could at the end of a chapter. But usually there's at least a little set somewhere I think are useful. So, chapter 1, exercises. I'm just looking for the numerical stuff. It's not chapter 1. Since I'm going to give you that chart, a question like this, I probably wouldn't ask. All right, this one. No, one that we can calculate. All right. Oh, I guess I didn't mention, maybe y'all know this, but when you do put something in scientific notation, you only put the significant figures that exist here. So this is telling you just straight out that that's going to be 3 significant figures. And it's still 3 even after you do this. So it's showing you 3 significant figures, and then when I put it in standard scientific notation, it's still showing 3 significant figures. I think these will work. Practice questions. 1.45 and 1.46. .47. 1.48. I better write these down. What did I say first? 1.45. I think those are all, as long as they're not asking you a bunch of crazy weird stuff. Diameter of the Earth, 1.48. Yep, so I didn't cover addition, subtraction. I guess I'll do that. I didn't have it in my PowerPoint. Pretty sure there's some simple calculations in here. All right, I'll pull out some more of those. Multiplication division rule. You ignore the exact numbers, and then you look at the inexact numbers. The one with the least number of significant figures, that's how many significant figures your answer has to be. When it's addition, subtraction, just remember this right off. It's not about significant figures. Addition, subtraction, it's not about significant figures. $231.6. When it's addition or subtraction, you look at how many numbers are after the decimal, and you have to use the one with the least least number of digits in its decimal in your answer. It's not about significant figures. 4 significant figures there, 4 significant figures there, but I'm not even going to think about that. I do this in a calculator. Okay, so here's what, so again, I'm going to write down everything my calculator gives me. 236.24. And then I'm going to work with it from there. 1 after the decimal, 2 after the decimal. So I need that to be my last digit. I'm still going to look at, so I'll underline these like that. I'll still look at the 4 to see if I have to round, but I don't. That would be the correct answer here. 246.2. I don't have any units up there, I just, let's put that in scientific notation, standard scientific notation. How many places do I have to move the decimal? She locked out?
Yeah.
Let's put this back up. How many places do I have to move the decimal?
2.
You said 2, right?
Yes.
It helps which one you put, the negative here or the positive here. Whichever one I want to apply here to move it kind of helps your brain a little to put it first. But of course, I'm just going to do this. That gives me that. So now I've got the decimal in the right place. And then this just comes down. You're never going to screw up whether you do negative or positive here if you do it that way. That's why I like my way. I don't have to think. It's that extra think you have to do that messes you up. Yep, that's right. All right. So addition, subtraction rule. So you can do. Did I write those down? I'll give you a list of this online. I think all those are good for practice. I'll do a few of these on the board though. I'll make a list of that outside of class rather than stand here and stare at it. Then I'll tell you when I have it. But let's do some of these. Man, I hate working on this chalkboard. What should we do here? Meters per second. Yeah, let's do one of these with time. Let's do 1.57a. A bumblebee flies ground speed of 15.2 meters per second. Okay. Let me tell you this. So that's what they have there. This is how they have it written. Meters per second. 15.2, and they put the meters per second like this. It is always, always, always true that when you have something like this numerical value goes with this unit on top, and this unit on bottom has a 1 with it, and that 1 is exact. What I'm saying is, whenever you see that, that's how we put it in text if it's in a Word document or something. But when you're ready to use that in a little piece of math, always do this. Meters, 1 second. That's the way you want to use it in math. This does equal that. They're the same thing. And this is inexact, and this is exact. This part's inexact, this is exact. You won't consider that for significant figures, but that's 3 significant figures. Okay, so a tip for you. What are they asking for? Oh, we need kilometers per hour. Okay. Somewhere over here, some number kilometers 1 hour. So we just have to cancel the meters to kilometers, so we need meters kilometers. That'll get us to kilometers, and then we need seconds to hours. I want more space here. I'll just go ahead and write this. 1 kilometer is 1,000 meters. I could have done 10 to the 3 here. I just decided to write it as 1,000. I bet that doesn't really show up on the... Okay. Seconds to hours, so you can do it like this. I need the seconds to cancel. So I'll put that on top. There's 60 seconds in 1 minute. And then, and then I'm going to need minutes to cancel out to hours. 60 minutes in 1 hour. That does it, right? Cancels the seconds, 60 seconds per minute, 60 minutes per hour, that cancels a minute, that'll do it. I didn't do any that have the time units in it, but you already know there's 60 minutes in an hour and 60 seconds in a minute. What do you think is exact here and what is not? I'll go ahead and tell you, this is inexact. That's that number that somebody made up out of the blue to create
Literally everything else?
literally everything else.
Okay.
Metric to metric, always exact, so you don't have to consider those for significant figures. And yeah, these are like the English units, the English to English. It's exactly 60 seconds in one minute, no more, no less. Exactly 60 minutes in an hour, no more, no less. So these are all exact. These numerical values. What else can I ask? So this means and this is exact too. This one with the seconds. What else can I ask? Our answer needs to be in 3 significant figures because this is all we have to consider now. Depending on how fancy of a calculator you're using, the way I do these in a calculator, we're going to calculate this. I would go 15.2 times, I'm not going to bother with the 1, 60 times 60, that's it. Now I'm going to say divided by 1,000 equals. I get as a numerical value I need it to be 3 significant figures, so that's all I'm going to keep. The 2 does not round to 7, so the 2 has to go away. I have this, and all of this cancels out to kilometers over 1 hour, aka kilometers per hour. So the answer, you could write the answer like this. Man, it is hard writing on a chalkboard. That should say kilometers, but it just looks like chicken scratch. You guys okay with that? In terms of problems to practice, I think most of what's on this page works. But do realize I'm going to give you conversion factors. I'll even give you that metric chart. Just be able to do calculations. The calculations can get a little more complicated. But I'll make a PowerPoint that does a little more. So I think we're going to end up going over more calculations Thursday. What else should we do today? I think.
And like, we leave the homework, I was like, actually, I'll put the table.
Maybe we could stop early. Maybe we could stop early. Okay, so I'll put together a good set of these to practice for calculations. That'll be you practicing for the test. Also, I don't think we have to go to lab. If you guys can watch that movie and answer the quiz. How many of you guys already did the quiz? There was only a couple of you that didn't. So between now and Thursday, get online and watch that movie and take the little safety quiz. And then we won't have to go to lab. Practice some of these. I'll make a full list. But you need to be, so the things from this chapter is, okay, yeah, it's the calculations, it's unit conversions, it's stuff about significant figures, it's stuff about addition, subtraction rule, multiplication, division rule. If you can do all that at the end of this chapter, then we're pretty well set to start doing chemistry instead of continuing with calculations. But we'll do more on calculations Thursday. So go ahead and start practicing so you have questions to ask if you have any. I think we'll just stop there. Everybody signed? Everybody signed this that was here? So it's Edwards, Jackson, Kenny, not here. Okay, y'all look at those problems and start practicing. Have questions for me? If you have questions, you ready to go over those? Are y'all good?
So
Everybody
no
good?
lab today?
No, lab was just watching the video and taking the safety. Right? That's what it said. So just do that at home. Watch the video. There's really no reason to go up to the lab. All right, I'll see y'all Thursday. We will go into lab Thursday.
I think I signed those sheets.
Sign what?
It said Jackson McClendon didn't sign.
Oh, yeah, sign if you didn't.
Hey,
Hey,
I won't be able to be here next week. I have like a family trip that I can't get out of.
okay, is it a whole week?
Yeah, so I'll miss those two labs. And I was looking